Hello everyone, welcome to yet another Flat Earth video. This one was inspired by Calvin Stroud, a flat earther who claims that on a spherical Earth, walls of a building must either deviate significantly from a plumb line if they are all perpendicular to the building's ground plane, or buildings must be wider at the top than at the ground. He got some attention on YouTube for promising a £10,000 prize to anyone who, well, let's hear it from the man himself.
I'm offering £10,000 cash to anyone who can dispute this, how the water level works, or how the spirit level works.
Nobody doubts that water levels work. Earlier in his video, Calvin gave a really nice demonstration and did actually a good job at explaining how they are used. What I can do though is to demonstrate why his water level does work on a spherical Earth. But Calvin isn't done yet. This is his second offer.
I'm offering £10,000 cash to anyone who can show me how you measure the curvature of the Earth. Because all the tools that I know only measure and work on a flat Earth.
This is definitely something we can give a try. So we have two things to do now. First, we need to clear up some of the misconceptions that Calvin has about angles in a building on a spherical Earth, from which he draws his weird conclusion that water levels wouldn't work. And secondly, we have to show how to measure the circumference or the curvature of the Earth using only the tools that he as a construction worker has access to.
So now you can see this angle of the roof to the wall has changed from 90 degree to 75 degree. If we're going to keep this one at 90, this wall has now changed to 75 degree. And if you come to the floor, it's 77 degree or 105 degree. It's the 105 degree one off this line actually. So you can see you don't make houses or buildings that shape. You can do these experiments yourself. It doesn't have to be to scale. You cannot have 90 degrees on buildings on a round Earth.
Or can we? A bit more than a month ago, Sciman Dan basically destroyed Calvin's entire argument with one single sentence.
Sorry, but if we're talking angles and things like that, then scale absolutely matters.
So I guess that's settled then, and why would anyone bother anymore? Well, first of all, Calvin asked his audience to
do the maths.
And doing the math is always a good idea and makes even flat Earth videos interesting sometimes. And secondly, Sciman Dan did not answer Calvin's question, which was how we can measure the circumference of the Earth or the curvature of the Earth. Now let's examine how significant Earth's curvature really is for the architecture of a skyscraper. To model his scenario, I used an open source application called GeoGebra, a portmanteau of the words geometry and algebra. It works basically like any computer-aided design program, except that it's written for learning and teaching mathematics from school to university level, not for engineering purposes. It's freely available, so anyone who's interested can reproduce my calculations with it at any time. Here's what this model shows. We start with a sphere with radius r and place a building on it. The building stands on a rectangular ground area with west-east dimension w1 and north-south dimension w2. There are two versions of our building. One has walls that are all plumb in their respective position, so there's a straight line going from the sphere's center through a bottom corner to a top corner. The other building is a cuboid with walls that are parallel to the plumb line in the center of the ground area. We can then calculate the difference of some angles, the width at the top, etc., and see how they change for different planet and building sizes, and if and to what degree scale matters. First, we need to prepare our construction site. A rectangle that will be the building's ground area. Its four corners are placed on the surface of our sphere, and we use two variables for the distance in north-south and east-west directions. Of course, we'll have to flatten our construction site before we can place our building on it. Not only are rubble, debris and boulders lying around here, due to Earth's curvature there's also a bulge that we need to remove, and of course we want to know how high exactly it is. Once our construction site is cleared of bulges and debris, we can build our skyscraper. We calculate the coordinates of the 4 top corners for both variants and paint the walls of the cuboid red and those of the building with the vertical walls green. And we can immediately see that Calvin is onto something. The green building is indeed wider at the top than at the bottom. To calculate the angle between its walls and how they differ from the angle in the red building, we construct lines that go from the Earth's center to the middle of the eastern and northern wall. The angles between these lines and the normal of our ground plane are what we're looking for. And that's our model. It's as simple as that. All that's left to do now is put in the right numbers. We'll increase the radius from our current 20 kilometers and the altitude of the building to, let's say, 500 meters and see what happens and how the angle changes. At 60 kilometers radius we can see that for a 100 meter wide building in north-south direction, the angle between the northern and southern wall has shrunk to less than 0.05 degrees. The difference between the top and bottom edge in north-south direction for a 500 meter high building is 83 centimeters, and the bulge that we have to remove during the flattening of our construction area is about 10 centimeters. We can now increase the radius to 600 kilometers, and unsurprisingly, both the difference between the top and bottom edge and the angle shrink even further. The angle between the northern and southern walls, which are 100 meters apart again, is now at 0.005 degrees, and the difference between the top and bottom edge is now at 83 millimeters. The bulge has also shrunk to 1 centimeter. But of course, in the spherical Earth model that Calvin wants to disprove in his video, the Earth radius is closer to 6,000 kilometers than to 600, so we'll increase our radius by a factor of 10 once again. And as you can see, at an Earth radius of 6,000 kilometers, the angles between our walls have become so tiny that we can use the small angles approximation and say that every time we multiply the Earth radius by a factor of n, the angles get divided by that factor n, and so does the difference between the top and bottom width of our green walls. So by increasing our Earth radius by a factor of 10, we decreased the angles between the northern and southern walls, which are still 100 meters apart from each other, to 0.00048 degrees, a tenth of what it used to be at the stage before, and we need more decimal places to accurately display it. The difference between the top and bottom edges for our 100 and 200 meter walls have shrunk to 8.3 millimeters and 16.6 millimeters respectively, and the bulge is at only 1 millimeter now. Now, what precision would Kelvin have to measure his angles with to distinguish a flat Earth from a spherical Earth using his water level? And of course we can calculate that easily by reducing our building dimensions to a ground area of 3 by 1 meters and a height of 3 meters, which seems to be a reasonable approximation for Kelvin's closet. And when we put these numbers in, we can see that the angles between the walls that are 3 meters apart are roughly a millionth of a degree times 14. The difference between the top and bottom corner of his cupboard would be 15 micrometers, and the bulge that he would have to get rid of to have an even ground for his cupboard would be 200 nanometers. That's, by the way, less than half the wavelength of his red laser. Now that we know that Kelvin's setup is inept to distinguish a flat Earth from a spherical Earth, if the precision of your measurement is limited by the wavelength of the visible light spectrum, we need to think of something else. Is there a simple method that anyone can use to measure the circumference of the Earth at a reasonable accuracy? And indeed, there is one. But this will be the topic of the next video. For now, let's end this one with the conclusion that water, spirit and optical levels can absolutely be used on a spherical Earth. A big thanks to anyone who watched and to the open source software community that provided the tools to make this video. Have a nice day. See you next time when we explore how to measure the circumference of our planet.